before we actually begin. All right, first, at least one of you are Lawson students. Nicole, are you Lawson students? I thought so, okay. You're a transit.
No, I'm Lawson.
Oh, you are Lawson?
Yeah.
Oh, have you just recently joined us, or have you been here a while?
This is my first semester.
Oh, really? Okay. Just incoming, or?
No, I guess I'm technically a transfer student, but I mean, I'm full-time here.
Okay, yeah, okay, but are you going to be full-time here in the fall, too?
Yes.
You are? Fantastic. Well, then this is for all three of you and anyone else listening who's a Lawson student, not a transient student, okay? Ms. Nyla Gerasi is our one of our math instructors, full-time math instructors on the Birmingham campus primarily. And she is also the coach of the math club math team, okay? And they are meeting this summer every Tuesday afternoon from 4:30 to 5:30, okay? Over on the Birmingham West campus in the science building, which is the little, are you familiar with this Birmingham campus at all?
Yeah.
You are? Okay. Okay. You know where the quad is in the middle?
Yeah.
Okay. Okay. The C building, the science building, is a little section that connects the B building to the library building on this end, not the administration building, but across from that. Very short in C100. Okay. That's toward the library end of things. Okay. And meets there every Tuesday afternoon, 4:30 to 5:30. They have a good time. They get ready for the competitions that's coming up in fall, but they also just have a good time as the math club and team. Okay, so please participate in that. All of you. You're the kind of people she needs, because when they have the math competitions, those with the most math usually win. Okay, and you have more math than what anyone else in the competition will have. Okay, now this is one they sent us around to announce, and I know sort of why, because we're trying to always get jobs for our students, okay? And we want the students to start looking toward jobs. But this is a private company, and I don't know, I have a little ill feeling of public institutions supporting specifically private companies. I think what they're doing is good, but I don't think we should be the sponsors or anything. But anyway, the name of the company is STEM Jobs. Of course, STEM stands for Science, Technology, Engineering, and Math. So these are the jobs that you will be having. The subtitle, Do What You Love. Evidently, this company, STEM Jobs, has released a new tool to connect classrooms to careers. It's the STEM Type Navigator. Allows students to match their interests to the opportunities. It says after high school. I believe it's more after college. Later they'll say after post-secondary, so I think that's what they mean. This company seems to be based in Pittsburgh, and I don't want to, opportunities for post-secondary institutions, employers, and the military. STEM jobs as long as, okay, blah, blah, blah. I'm just going to let you read the rest of this. It sounds good. I have no problem with what they're doing. I just don't know if we should be advertising it. But they said to, so I'm doing it. So you're welcome to come take a look at either one of those, take notes off of them. Use it. That's what they're there for. Okay. Any questions on math type stuff, calculus stuff? Okay, if you recall from last time, if you were here or if you watched the video, we're in section 8.5, chapter 8 is integration techniques and improper integrals. We're going to stick with mostly the techniques. And 8.5 deals with partial fractions. And we did an example 3, which was on the slide set, and also at larsoncalculus.com for an interactive version of that type of example. But example 4 is at neither. So let's proceed with example 4. If there are no questions, any questions? Anything we've done so far? Say again? Say that one more time.
I was wondering if we could do example 3 again.
Do what again?
Example 3, because that's missing.
Okay. We certainly can, especially if we do it fairly quickly. What do you think, folks? Okay. So I'll erase that ink I just drew. Okay. Now, the method of partial fractions works for rational functions. Now, what do we mean by rational functions? Functions with polynomials in the numerator and polynomials in the denominator. Okay? Now, what's the first test? The first thing you do before you start trying to do partial fractions? Evaluate the degree of the numerator and denominator. What's the degree of the numerator? 3. What's the degree of the denominator? 4, because if you multiply, see, they were very nice to you. They factored it, or at least did an initial factorization. They don't have to. They did it in this case, but if you were to multiply it back through, which I don't suggest you do, that degree would be 4. Okay? Now, in order to use the method of partial fractions, the degree of the denominator must be greater than the degree of the numerator. In other words, the degree of the numerator must be less than the degree of the denominator. This fits the bill, so we can proceed. Okay? Next thing we do, once we found out we can use partial fractions, what's the next thing to do? Factor the denominator. They've already started it for us. Can you factor this one any further? Not that one. This one, what can you do? Okay, factor an x out of it, and that would give you x times x minus 1 times x squared plus 4. Okay? Guarantee you, and by the way, here's what they say. You have all linear factors are irreducible quadratic factors. That's an irreducible quadratic. You can't reduce it any further. Okay. And let me get Davis here, right? Okay. There you are. All right. Bottom part of the alphabet, doing fairly well. Top part is completely missing. I don't know where they are. Okay. Must be starting the 4th of July holiday early. Which, by the way, y'all did hear the good news, bad news situation, right? Okay. The bad news is we missed a day this week. No, I'm sorry. The good news is 4th of July is this week. The bad news is we missed class because it's Wednesday. Sorry about that. Get over it. Okay? There will be no class on Wednesday. Okay? That's the bad news. Second?
So I thought we were going to get into the test on Wednesday. That means you're on Monday?
Okay. Okay. You did get your first test already, right?
Yeah.
Okay, right. Okay. The second test will be when we finish this section. This chapter, not the section. But we're getting pretty close. Okay. So, anyway, no class on Wednesday. Now, that does lead to one other announcement I forgot to make. I'm not going to say that our administration is slightly anal retentive or anything, but because the 4th of July is a holiday, we technically get 8 hours off on the 4th of July. But since we're doing 4 10-hour day weeks, that means we still owe the school another 2 hours for Wednesday. Okay? So what that means is for each of the 3 days we are working this week, I will be working an extra 40 minutes. Okay? So like today, normally my office hours would be 2 to 6. They will now be 2 to 6:40. And then on Tuesday and Thursday both, I end the day over on the Birmingham East Campus, and usually I have the last 30 minutes of office hours over there, though I'm not in an office, I just am in the classroom. Can't think what the K103 is, the Ethel Hall building on the Birmingham East Campus. Normally I'm there from 5:30, the class ends at 5:30, so I'm there until 6. From now to tomorrow and Thursday, it'll be 5:30 to 6:40. So I'll be there an hour and 10 minutes on both of those days. Okay? So I should have announced that earlier. I forgot. All right. So the next thing we do is factor the denominator. Okay, now what do? We take this fraction, this partial, there's a rational expression that's in our integrand, 2x cubed minus 4x minus 8 over the factored form x times x minus 1 times x squared plus 4. Now there's a couple ways you can go from here. Well, no, yeah. Here's how you go. One way from here. If you can break this into partial fractions, that will be a over x plus b over x plus x minus 1. I can't read my own writing here. X minus 1 plus c over, no. Let me write down the denominator first. X squared plus 4. Let me back up just a moment. That's not finished yet. Notice this portion, this factor of the denominator is here. Since the degree of the numerator is less than the degree of the denominator, the degree of this numerator must be less than the degree here, so that just is a constant a. Same thing here. Here's this factor, x minus 1. The degree of the numerator must be less than the degree of the denominator, so it's just b. But this one, the denominator is x squared plus 4. So its numerator must be at least 1 degree less, so that would be what? Cx plus d. Okay, that is how we set up our partial fractions. Okay, now, next step. I'm not sure the book does this one, but it sure makes life a lot easier. Since you have denominators, and we don't really like denominators that much, do we? Let's multiply everything on both sides of the equation by that entire denominator, common denominator. It's x times x minus 1 times x plus x squared plus 4. I can't write. X squared plus 4. Multiply this by x times x minus 1 times x squared plus 4. Multiply this one by x times x minus 1 times x squared plus 4. And multiply this one, yuck, I don't have room, by x times x minus 1 times x squared plus 4. Okay, that's supposed to be up top. Okay? Now, and over here on the left-hand side, everything in the denominator disappears. Okay? Leaving us just 2x cubed minus 4x squared minus 8 is equal to, now over here, the first term on the right, the x's are what we lose. But that's all. Leaving us a times x minus 1 times x squared plus 4. Plus, and the second term here, the x minus 1's go out. That leaves us a b times x squared plus 4. Okay? And in the third one, the x squared plus 4's go out, leaving us, whoops, forgot my plus sign, plus cx plus d times x minus 1. All right. Now, here's the rationale. This polynomial equation is supposed to be good for any value of x, they say. Right? Now, I have some real problems with it because usually when I write down something that starts like this, I immediately think to myself, x can't be 0, x can't be 1, because that would make your denominator 0. But those are exactly the values we're going to plug in here, which seems unfair, but it's doable. Okay? So let's do it. Pick a value for x that's going to make one of these terms go to 0. Any value of x. Second? 1? Is that what you said?
Yeah.
Yes, x equal 1 will do it. So in this our first step here, we'll say let x equal 1. Okay, the left-hand side becomes 2 minus 4 minus 8. It would be 2 minus 12 would be minus 10. Okay, and Connor's here. And Justice is here. I know you're in here somewhere. There you are. Okay. Okay. Anyone else going to use the color? Okay, we're reviewing example 3 from the last time, so you haven't missed anything if you were here both mentally and physically last time. You will have seen this before. So on the left-hand side, when you let x equal 1, that'll be a 10. What happens to the first term here? It goes to 0. Over here, plug in x equal 1, and you get plus b times 1 is b. 1 would be 1 squared is 1, plus 4 is 5. B times 5 times 1 is 5, so that is 5b. Plus, and here when you let x equal 1, that goes to 0. So you have I can't talk. 5b is equal to negative 10. What does that imply? It implies that Bailey's here. Okay? All right. And we're just, if you were here last time, we did example 3, but I was asked to repeat this, so we're doing example 3 again. What this implies then is b is equal to what? Negative 2. All right. Give me another x. That would be real easy to evaluate and maybe rid yourself of some problem issues. X equals 0. That would certainly do it. So now we'll let x equals 0. What do you have on the left-hand side? Say again? This one up here. Say again? Negative 8. Got it. Negative 8 is equal to, and if x equals 0 over here, the first term's of minus 1, the second term's of 4, that'd be minus 4a. Right? X equals 0 here, sends that to 0. X equals 0 here, sends that to 0. Whoa! That means negative 8 is equal to negative 4a. So what does that imply? A is equal to 2. Right? And I forgot, this is not how I did this problem before. How I did this problem before was factor out a 2 and put it outside the integral. I just have noticed I should have done that already, but I didn't. Sorry, I forgot that. Guess what? There's nothing else easy to do. But you've got down to the point where the whole thing is fairly easy. Okay? I'm going to try to get rid of these if I can. All right. Let's plug in what we know. Okay? Here we have 2x cubed minus 4x squared minus 8 is equal to, a is 2, so that will be 2 times x minus 1. Let's just multiply those out. Why carry them around any longer than they have to? They get heavy after a while, so let's not carry them any longer than we have to. Okay? Let's FOIL this and see what we get. X times x squared is x cubed. And then a minus 1 times x squared would be negative x squared. Okay. A 4 times x would be plus 4x. And then a minus 1 times a 4 would be minus 4. Okay, b was negative 2. So it's going to be minus 2. And let's multiply that through. And what do we get? X cubed plus 4x. Right? Plus, and this one we can't do much with. So I'm going to first multiply these two together. X squared minus x. Okay, and then we'll FOIL these two. cx times x squared is cx cubed, and d times x squared would be plus dx squared, but cx times minus x will be minus cx squared, and d times minus x will be minus dx. That's kind of ugly, but doable. All right. Well, let's see what we got here. 2x cubed minus 4x squared minus 8 is equal to 2x cubed minus 2x squared. This is why I wish I had gotten rid of my 2's when I could have. Plus 8x minus 8. I can't multiply. Minus 2x cubed plus 8x plus cx cubed plus parentheses d minus c times x squared minus dx. Okay. Now, what I suggest we do right and left is, well, on the right, let's combine like terms. 2x cubed minus 2x cubed goes to 0. I missed something here. Minus 2 times 4x is minus 8x, not plus 8x. And you didn't catch me. Why not? Okay, that's what you're there for. It's to catch my errors. Okay. And what we're left with, without doing anything else, is notice that c x3 x cubed has to be 2. So this tells us c is equal to 2. Okay? Yeah, and this is how the book did it too, and they got the same answers. Now, just to make a confession to you, just because I do find that every now and then I make an error, okay, as you just seen, I like to check them and make sure everything's consistent. So we got through with the x cubed terms, so I'm going to wipe those out. Let's look at the x squared terms and see what we get. A minus 4 here, and over here we have a minus 2 equal to minus 2 plus d minus c. Those are your x squared terms here. Well, let's see what we get from that. Oh, we had to do this because we didn't have d yet. Okay? But c is 2, so let's take off the c there and make it a 2. I forgot to do that. Okay. Well, this is minus 2. Minus 2 is minus 4. Add that to both sides, you get d is equal to 0. Is that right? No. What did I do wrong here? Well, they did it slightly differently. Okay. But we should get the same answer, and I'm not getting it, so I've done something stupid here, and I can't see what it is. Can anyone see where I messed up? I'm right with them, all except the D. They get D equal 4, I got it equal to 0. I think I know where it must be, but I haven't figured out how to get it there yet. Okay. Okay, on that last term we got in two different ways I get D is equal to 0.
It's 4x, not 4x squared on one side, right?
Say that again?
Like on the original equation, it's minus 4x.
Oh, that may be it. You're absolutely right. No wonder it wasn't coming out right, because I wrote the problem down wrong. And this is the first and only place that I use that. Sorry, that's it. That's out, that's out. Okay, let's start over. Whew, thank you. I was checking all my math. It wasn't my math, it was my copy skills. Oh, wait, one more. That one's out. Okay. But we hadn't used that yet until right there, and that's where it was. Okay. So the x squared terms are 0 is equal to -2 from this one, and plus d minus 2 from that one, and that would yield us d is equal to 4, which is exactly what we got, the book got. So c is equal to 2. Did I erase that somewhere? Yes, I did. Okay. This gave us c is equal to 2. D is equal to 4. Okay. Now let's look at the x terms. Yuck. I'm going to have to go up here. I can't get my pen to write. This thing drives me nuts sometimes. It's lost in space somewhere here. I'll try that and see what happens. Okay. We got to wait for the program to respond. Now, I don't know why it's not responding. It's just going around in circles. I know what happened when I was trying to write down here. These icons weren't showing up. I went to write, and then when I start trying to do something, so it's trying to expand something or do something, and it's lost what it's doing. So I'm going to try this. This sometimes works. Okay. I'm going to do Control Alt Quit. I may have to start over. Sorry. It looks like it's going to. Okay, finally. That's what I was trying to get to. Sometimes if you go back to this, oh, they're not responding, so I think I'm going to have to close the program. Microsoft PowerPoint's not responding, so it's probably a PowerPoint problem, not mine, though I think I led to it. Sorry about this. So we got the same thing they did. A is equal to 2, B is equal to -2, C is equal to 2, D is equal to 4. Now, don't want to really go back and do all the rest of them again. But what you do is plug those into your original assumptions here. A is 2, so it would be 2 over x plus B minus 2 over x minus 1 plus 2x plus 4 over x squared plus 4. Okay? Okay. I'm so sorry. Do you think you can go from there, or do you want to see the rest of it worked out? Huh?
Yeah, you're fine.
Okay. Sorry about that, but it just lost its mind. And let's go back to current slide. Okay. So what we're going to do at this point is go on to example 4. Hopefully it'll work out a little bit more smoothly. So let's do example 4. Sorry, my pen gets all wadded up, so I have to straighten it out a little bit. Okay, here's our new integral. 8x cubed plus 13x over x squared plus 2 squared dx. What's your first step to do before you try anything to do with partial fractions? What do you have to verify? You have to make sure it's the case. Power of the numerator has to be less than the power of the denominator, the degree. What's the power of the numerator? Third degree. Denominator? Fourth, because x squared squared would be x to the fourth. So yes, we've got an improper rational expression there. That's what you, a proper rational expression, where the degree of the numerator is less than the degree of the denominator. Okay, that being the case, what do you do next? Rewrite this the integrand as 8x cubed plus 13x over, and I'm going to write it, it really doesn't matter. Let's leave it the way it was, x squared plus 2 squared. But what's going to be your attempt? Okay, ax plus b over x squared plus 2, that's the first one, plus cx plus d over x squared plus 2 squared. Anytime you have a multiple in the denominator, you have to write the numerator over to the first power, then to the second power, to the third power, up to the nth power. Well, this one is 2, so we go up to 2. Okay? But you have to, because both of those are irreducible quadratics, you have to have a linear numerator. So ax plus b and cx plus d. All right? Now, the next thing you do is multiply by your denominator. X squared plus 2 squared. X squared plus 2 squared. X squared plus 2 squared. Okay? Here, you get rid of all your denominator. Here you get rid of one of those terms. And here you get rid of them all. Okay? So what does that leave you with? 8x cubed plus 13x is equal to, on the left, we have a product of two binomials. So what does that give you? First times first is ax cubed. And then let's do our squared terms. That would be this one plus bx squared. Our linear terms, that would be these two, to ax, and our constant term, say again, or not to be, plus 2b. All right. And then over on this side, all we've got left is a plus cx plus d. Right? Everybody in agreement? Okay. Now, let's start with the cubic terms. 8 x cubed has to equal ax cubed. What does that mean a is? A is equal to 8. Whew, that made life a lot easier. Now let's look at our quadratic terms. This is working out way too easily. Am I doing something wrong? I guess not. Okay? Guess what b is? Do you see a quadratic term on the left? It's a 0. Okay? All right, those are done. All right, linear terms. Here we have a 2ax, so let's start with 2a plus c is equal to 13, right? But a is equal to 8, so 16 plus c is equal to 13. What do you reckon c could be? -3. All right, that's done. That's your linear terms. Okay, actually, well, no, we still got one more, so let's do it. What's your constant term on the left? 0 is equal to, and your constant terms on the right? 2b plus d. But b is 0, so d is 0. That seems way too easy, but let's see what it yields for us. That makes that integrand, this thing here is equal to, a is 8, so let's put on the a to the outside. That would be x over x squared plus 2 dx plus, make that a minus, minus 3, that was your c, times the integral of, because the d was 0, x over x squared plus 2 squared dx. Now, did I do everything right there? Catch me in any errors? You should have, but if I did it. Okay. Now the question is, how do you proceed to try to do a integration like that? What would be your approach? Substitution. What would you substitute? Let u equal x squared plus 2. Is that what you said? I like it. Then du is equal to 2x dx. Okay. I want a 2 in there. So I'm going to take a 2 out of here and make this a 4 out here and bring the 2 in there. Okay. I'm liking that okay. This is not a definite integral, it's indefinite. Okay, how about the next one? I'll come back and finish that in a minute. What about that next one? I kind of like the same thing, don't you? Let u equal x squared plus 2. Then du is equal to 2x dx. Okay. Now I want a 2 in there, but I don't have it, so I have to multiply by 2 and divide by 2. That's legal in most states, right? Okay. So we got that done. All right, let's see what we've got here now. What we got here is 4 times the integral of, this was 2x dx is your du over u. Minus 3 halves, what do you have here? The integral of du over u squared. Okay? Now, hopefully we can do that first one without too much further ado. What is it? 4 times the ln of u. Okay, now remember, well, our u's are the same thing, so it's not anything. Sometimes u's might be something else, so remember which u is u. Or change one of them to a v or something else. But these u's are the same, so it's okay. But on that second one, I'm going to rewrite the integral slightly. Minus 3/2 times the integral of u to the minus 2 du. What would that yield? Antiderivative would be, second, okay, minus u to the minus 1, so the minus is going to take out that. That'd be a 3/2 u to the minus 1, right? Okay, and then we'll have somewhere out there a plus c. Okay, now there's our answer, except it's in terms of u's and the problem was in terms of x's. So I'm going to go to the top and write our recommended solution to this. That integral would be 4 times the natural log of, guess what? X squared plus 2 is never negative, never 0 for any real value of x, right? So we can lose the absolute value sign. And just write x squared plus 2. Okay? Then we have a plus 3/2. Okay? I'm going to just put that over x squared plus 2. Let's put that in the denominator, plus c. There is my hope of what the answer is, and let's see what they got. 4 ln x squared plus 2, good for them, plus 3 over 2 times x squared plus 2 plus c. Yes, there's our solution. Any questions on that? They do have a technology blurb at the bottom that shows you can use a graphing utility to confirm the decomposition found in example 4. And what you do is graph the first integrand as y1 and the second integrand as the new breakdown that we did, kind of, and you'll get that those are indeed the same. Okay. Now, I've been saying this all along. I think they're just sort of catching up with it now. When integrating rational expressions, keep in mind that improper rational expressions, and here they give one. All right, to erase this. Okay. Okay. Here's your expression. N of x over d of x. Cleverly meaning numerator of x over denominator of x. Both of these polynomial functions. If this is what you had to begin with, 2x cubed plus x squared minus 7x minus 7 plus 7, okay, over x squared plus x minus 2. What's your first step? That was your integrand. What's your first step? Second? And what is it? Bad news bears. So what do we do? Second? Long division. Divide that denominator into that numerator. 2x cubed plus x squared minus 7x plus 7. I hope I'm not getting any signs wrong. How do you do that long division? Does anyone remember that? Yeah, just like regular. X squared will go to 2x cubed. Now, that's the thing. Division, you start left and go right. Addition, subtraction, multiplication, start on the right and go left. This is one you start on the left and go right. So x squared will go into 2x cubed how many times? 2x times. Then you multiply. 2x times x squared is 2x cubed, but you also multiply 2x times x is 2x squared, and you also multiply 2x times minus 2, second, minus 4x. Time out just for a moment, folks. Before you do long division of polynomials, make sure that you have every power accounted for. 3, 2, 1, 0, blast off. 3, 2, 1. Make sure. If you don't have them all accounted for, be sure you inject a 0 coefficient with the one you're missing. Like if this had been x to the fourth here, you'd have done 2x to the fourth plus 0x cubed plus x squared. You'd have to account for every term. Okay? We did. I didn't even think about going back and telling you that, but we did. Okay? Now what you do? Subtract. But you got signed numbers, so I like to change signs and add. Same thing. So make that a minus. Make this a plus. Make that a minus. Ooh. And make that a plus. To me, it's easier to add signed numbers than it is to subtract them. That goes to 0. That's exactly what we wanted it to do. What's the next one? Negative x squared. Next one. Minus 3x. And then what do we do? Bring down the plus 7. Just like you did with division. Remember? Now, divide first in the first. X squared will go into minus x squared. How many times? Negative 1 times. Then you multiply. Negative 1 times x squared is negative x squared. Negative 1 times x is negative x. And negative 1 times negative 2 is plus 2. Okay? And again, I prefer changing signs and adding. So plus, plus, and make that last one negative. That's just because I make fewer mistakes that way. I make too many mistakes subtracting sign numbers. That goes away, and what are you left with? Negative 2x plus 5. Now, what do you do with that? What do you do with the remainder? Put it over your divisor. So that's going to be, let's make it a plus. I don't know, I like it a minus. So let's do a, that doesn't really matter. I really do like minuses better. I like my fractions to start off positive. That would be a 2x minus 5 over your divisor, which is x squared plus x minus 2. That's right. Remember, that's what we did. If you had a remainder, put it over the divisor, make it a fraction. Okay? Remember, that's what we're integrating. So guess what we do? We integrate the first this part, integral of 2x minus 1 dx, and then we'll do a minus the integral of 2x minus 5 over x squared plus x minus 2 dx. Okay? Guess what, team? I can integrate that. Okay? X squared plus 1, right? They're not carrying the problem all the way out. I'm just showing you how to. And then this one, we use partial fractions. You got the numerator lower degree than the denominator. First step done. And now you factor this, x minus 2 times x plus 1, and go to town. Right? Just like you would have done before. They don't carry all the way out, so I'm not going to take the time to. But you see, it's quite doable. But that's why when you do have an improper rational expression, do long division to make it proper. Integrate the first part, that polynomial you have, and then your second part, your remainder, you write as a proper rational expression. Sorry. And then do your partial fractions just with that. All right. Now, this week, sorry, I'm choking. Any questions on that before I go to the conclusion? Did we do this? No, yeah, we didn't get this far. By the way, Patrick, let me erase this. You'll hopefully see on the PowerPoint of last time, but this is how we carried it on through. The example 3 that we were starting on, I forgot they had it up here. They went on and factored the denominator, wrote it out just like we did, wrote out that big long thing by multiplying by least common denominator. We got A equal 2, that's what we got. B equal -2, that's what we got. C and D, just go back and plug in A and B values and see what you get. They went on and did another x equal -1. You can do that if you want to, or just plug in the values and match up coefficients. I found this a little messy, but it's correct. But I would just plug in what we knew already, A equal 2, B equal -2, and then have the regular coefficient on this, the regular expression on this side, and match up the terms. And they got 2 is equal -c plus d. I'm not sure. For x equal, goodness gracious. They are doing it a long way. You can do it this way. This gives you 2 equations, 2 unknowns, and then you solve for that. C is equal to 2, D is equal to 4. To me, that's much longer than the way we did, or would have done had we finished it. But this is what you wind up with then. And this is a log, right? This one right here, the first one, is a log, 2 times the log of x, minus 2 times the log of x minus 1. This is a substitution. That's just log of this thing, log of x plus 4. And then this one is an inverse trig, by the way. Messy but doable. And when you do all those in there, here's what you get. 2 times the log absolute value x minus 2 times the log absolute value x minus 1 plus 2 times plus log of x squared plus 4 plus 2 arctangent. I like to put inverse tangent, but they like arctangent. X over 2 plus c. Now, the rest of it is just making it look prettier. Okay? Oh, they didn't do it. Okay? I was thinking in the book they did, but I guess they didn't. They left it exactly that way, which is perfectly fine. Here then is what I thought we were going to go to next. Here are some guidelines for solving the basic equation that is obtained by partial fraction decomposition. Okay? Solving the basic equation. That's your, whatever was in your integrand, that rational expression form. For linear factors, substitute the roots of distinct linear factors into the basic equation. Basically trying to come up with zeros so you can eliminate certain ones of the unknowns. Okay? For repeated linear fractions, use the coefficients determined by the first guideline to rewrite the basic equation, then substitute other convenient values of x to solve for remainder. That's one way, or coefficients of similar terms. For quadratic factors, expand the basic equation, collect terms according to powers of x, that's what I was doing, equate the coefficients of like powers to obtain a system of linear equations involving a, b, c, and so on. Solve the system of linear equations. Okay? I don't see why having 2 sets of rules, both of them work pretty well. Okay? Now, any questions? That finishes 8.5. Homework exercises here. Any of the odds 3 through 19, all those are at calcchat.com, 7's at calcview. Do either 21 or 23 or both. They're both at calcchat. 21's at calcview. Do any of the odds 25 to 31. They're all at calcchat. None of those are at calcview. Either 33 or 35. They're both at calcchat. Neither are at calcview. And exploring concepts, you can do 37 or 39 if you'd like. If you find it less than conducive to do so. Actually, they're both pretty easy to do. All they're asking is choose a method. So I would do both of those. Okay? then do either 41 or 43 or both. 45 is a pretty good problem, but I would say any of the odds 45 through 49. Several different types of problems there. Just use one of those, or more if you like. And then again, 51 is, you have two different methods you could go from. Frankly, the partial fraction one really looks like that would be a pain in the neck to do. But I'll let you. You can mess with it if you want to. If not, go. All right. Now, I can't remember the verbiage at the beginning of the term on the course description, whether we did numerical methods or not. I'm thinking we do. So this is our throw at numerical methods. Okay? So let's do 8.6. I'll try to get through these fairly quickly. They're tedious. Basically, you can buy packages that do them for you. Okay? But it's good to know basically what the procedure is doing. All right. From current slide, let's go for it. Okay, still integration techniques, less on improper integrals. We'll probably skip that section completely. 8.6 is numerical integration. We're going to do, start by approximating the definite integral using a trapezoidal rule. Then we'll do Simpson's rule. Okay? And then we'll analyze the approximate errors for these two rules. Okay. Now, a lot of texts start with the midpoint rule, or maybe start with trapezoid, then go to midpoint, and then do Simpson's rule. This book kind of just skips the midpoint rule, which is actually better than trapezoid rule, and then you use the two of them to come up with Simpson's rule. This book doesn't do it that way, so we'll just start with trapezoid rule. Some elementary functions simply do not have antiderivatives that are elementary functions. Okay? Try this one. The product of those two. You're not going to find it, okay? Anywhere in any table, anywhere. Any of these are not doable by any technique that we've had so far. And guess what? Most of the ones you'll probably, if you ever run into an integral in real life, there's a real good chance it's not going to be integrable by any of the techniques we've done. If it's something really simple, yes it is, okay? But a lot of times it's going to be something oddball, screwy like this that you can't do as analytically. So what we have to do is do it numerically, okay? If you can't come up with an antiderivative, while the fundamental theorem of calculus is still true, it can't be easily applied. In that case, let's go to the alternate technique. The first of these is one way to approximate a definite integral is to use n trapezoids. Okay? And here's how it works. If this is your function f, okay, and it's one of those you don't know how to integrate. All right. Here's precedent. All right. Again, the bottom part of the alphabet doing quite nicely. Top part, two people here. Perfect. Okay. So here's your function f of x. Okay? It's one we don't know how to integrate at all. We don't have a clue. There's no formulas, no translation. There's nothing we can think of that will work. Okay? But you do know what the function is, and you can evaluate the function. You just can't integrate the function. So what we do is split the function from wherever your first point is. These are definite integrals, by the way. X equal a to x equal b. Split that into n equal segments. We're showing here n equal 4. So x of 0 is your A, x of 1 is a quarter way down, x of 2 is halfway down, x of 3 is 3/4 away, and then x of 4 is actually all the way to B. Okay? Now, like I said, you can evaluate the function. So you already know what f of A is, f of x1 is, f of x2, f of x3, and f of x4. You can evaluate a function, you just can't integrate. Okay? So with those values, we approximate the area under here, which is the integral of it. Now, of course, this has to be a function that's always greater than or equal to 0. Obviously, you can't. It's always positive on the interval a to b. Interval a to b. So, this area of that trapezoid will be the length here, f of x1 plus f of x2, that's b1 plus b2, times this, divided by 2. That is the area of the trapezoid. Because if you think of this, take this trapezoid, flip it over, and put it on top of this one, you have a rectangle, right? Put the long side here, the short side there, you have a rectangle. And then this area is length times width. The length is f of a plus f of x1, f of x0 plus f of x1, times dx, x0 minus x1 minus x0, times, and take half of that. And same thing here, and same thing there, and same thing there. Now obviously this trapezoid overshoots the function by just a little bit. This one undershoots by a little bit more. This one overshoots by a little bit more than this one, but less than that undershot. And this one's almost right on the money. It's undershooting it a little bit. It'll never be exact, but you come up with an approximate area under the curve. Okay? How do you get a better area? Reduce your triangle. Let's say go to 8. 1 here, 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 and here. And now you have much smaller trapezoids, but more of them, and you do sum those up again. Well, it's still not going to be exact. Keep going smaller until you get the precision you need. Okay? Again, you're not going back to an integral. You couldn't do the integral in the first place, but you get it to within whatever. So say this one got you within some number. Okay? And then when you did a smaller interval, like having of each of those, and you got something that was 2/10 better. Well, you want to be sure you're within 2 100ths, okay, or 1 100th. Well, just keep going down until your last estimate is less than whatever precision you're going for, difference from your previous one, and then say, hey, we'll settle for that, because they're not getting better to any more precision than what we've got. So, there's the procedure, okay? So first, partition the interval a to b into n subintervals, each of which, now here's the key here. Your delta x here is b minus a, that's the length from here to there, b minus a, that's that length, divided by n, and that would be how big each one of those is. That's your total length divided by n subdivisions, equal length, so that'll be your delta x, b minus a over n. Okay, now of course, your a is x of 0, and this is less than each one of those, less than x of n, which is b. Then form a trapezoid with each subinterval, and the area of each one will be f of x minus 1 plus f of x plus 1. That's those two added together, divided by 2. So basically, it's like the average between those two times your delta x, which is b minus a over n. Okay? So that's the area of each trapezoid, and sum them all up. Well, every one of them has that b minus a over n, so that's your delta x comes out front, b minus a over n. And then what you're doing, when you look at this, is the average of the first two, plus the average of the second two, plus the average of the third two, plus the average of the fourth, all the way up to the last one. And you'll notice here, you use f sub x0 only once, and f sub n only once. For all the rest of these, you use twice. So pull out the 1/2 and put it with the 2n here, okay, the 2 outside there, And then you have f of x0 plus 2f of x1, 2f of x2, 2f of x3, all of them till the very last one you only have one of those. Okay? And that's not that hard to calculate. So what you do, you know what your n is, okay? It's how many times you're going to do, and then for each of the values, now x of 0 will then be this thing added to f of 1 will be this thing added to f of n, twice that added to the other. So you come up with all those x values, calculate the f there. First one you just use it once, every other one you use twice, except that one you use once. Add them up, multiply them by that, and you've got your solution. That's a lot of blah, 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 right? And I don't know why in the world they go back to saying that's what you had to begin with. But that's what you had to begin with. I mean, if you did it all right, of course that's what you had to begin with. Okay? So here's the theorem. Let x be continuous on A to B. Notice here we include the endpoints. Okay? The trapezoid rule for approximating that will be you determine your n. Okay? And whatever it happens to be, whatever you're wanting to start with, let that be your n. Then your dx is going to be b minus a over n. Okay? And then you're adding up all these things because you had half of that one and half of that one. Pull out the two and just double the ones in between. And when you go, of course you have to evaluate the function at every node and then use that formula to give you your answer. And again, it's a lot of blah, blah, blah. Let's see what example 1 is. Use the trapezoid rule to approximate. Now we know the answer to this, don't we? We can integrate 0 to pi sine x, right? We can even mark Terrell here, okay, if we wanted to. Okay. And almost back. Anyone else come in since I called it? Okay? Now, by the way, people who came in a little on the late side of things after I made the announcements, there are a couple of announcements out there. One applies only to Lawson students, but the other one applies to any of you. So listen to it. I've got the materials up here. Come up after class and take a look at the flyers and see if you're interested. Okay. So we know the answer to this one. We don't need to use the trapezoid rule here. Okay? You want to go and figure out what the real answer is? It's not that hard. Yay or nay? A lot of apathy going on around here, okay? So let's, we don't have to do it, okay? But it said, compare the results for n equal 4 and n equal 8, okay? So here's what we do. Here's your functions. From 0 to pi, you know that's the sine function. You can't do it 0 to 2 pi because this is less than 0. You have to have this being above the x-axis. You can touch the x-axis in one or more places, but it can't ever fall below. Okay? Now, if you're going from 0 to pi and doing n equal 4, then b minus a will be pi. Pi minus 0 will be pi, divided by 4. So that would be, each interval is pi fourths. So that would be 0, pi fourths, pi halves, 3/4 pi, and pi. Those are your 5 function values there. Okay? When you're doing 8, you just introduce 1 in between each one. 0, pi, pi fourths, you know, like this. Every 8th of pi. Okay. Now, what you have to do here is do some evaluation. Okay? Sine of pi fourths. Anyone know what that is? Is root 2 of, where is my pen? Okay, I think I got it now. This is, value here is root 2 over 2. Pi halves, 1. 3/4 pi, root 2 over 2. Okay. Over here, I think you're going to have to use a calculator because I don't know this one by heart. What is sine of pi eighths? Sine of pi eighths. Be sure you're in radian mode. Probably a decimal number, right? What is it? 3, huh? 0.383. And that will be this one down here too, 0.383. Okay, and since you're there, do 3/8 pi. Second, 0.924, and that will be the same here too. Okay? That's for future reference use. Okay? Now, for the trapezoid rule, and I'm going to call this T sub 4, that's how they usually designate it. Your dx, so to speak, is pi fourths, right? Pi minus 0 is pi, divided by 4 is pi fourths. Okay. But we do pi over 2n, okay? B minus a over 2n to count for that 1/2 there. So let's make that an 8 rather than a 4. If you go back and check, you see that that is indeed true. 1/2 of your delta x. And then you do your alpha 0, which happens to be 0, plus 2 times the square root of 2 over 2, which is square root of 2. This is for L4. Plus 2 times 1 is 2. Plus 2 times root 2 over 2 is 2. Plus 1 times 0. Okay? So our approximation here is, I'm sorry? Oh, the third one, yeah, I'm sorry. I may have even said it, just didn't write it right. Okay. Okay. So basically this is going to be 2 root 2 plus 2 times pi over 8. And the 2's can come out, leaving that a 1, make that a 4. So this is going to be pi fourths times root 2 plus 1. Okay, so punch that in and see what value you get from that. Root 2 would be 1.414 plus 1 would be 2.414. Second? 1.896. Okay. There's our first approximation. Now let's do T8. Okay? Now, we've already got some of those. The 0, the pi fourths, pi halves, 3/4 pi, and pi. We already got those. And you gave me the others. And some of those are doubles. So let's see what we've got then. Our T8 is going to be pi eighths, but then divided by 2 would be pi 16ths times 0, okay, plus 2 times 0.383, and that's 0.766 plus root 2 plus 0.1824, 1.824. No, 44. 48. I don't know what I'm saying. I've lost my train here. 1.848. Yeah. You're actually going to have two of those, but we'll get back to that in a minute. Plus 2 plus then that again, 1.848 plus root 2 plus 0.766 plus 0. Okay. Goodness gracious, this is tedious. Oh, I like this so much. Okay. You got the calculators, you plug in the values. If I were doing it, I'd just say 2 times this, plus 2 times that, plus 2 times that, plus 2. That will do it. Whatever that turns out being, multiplied by pi divided by 16. 1.97. So T8 gave us approximately 1.97. Did you have one more digit? 4. Okay. Now, anyone want to make a guess about where we're heading on that? Or does it look like we're heading? And by the way, look at this. Every time the trapezoid is underestimating the real value. So the real value is something greater than 1.896, something greater than 1.974. But you see, we're getting awfully close. 2? Did I hear a 2? Would that work? Now I am going to evaluate this. What's the antiderivative of sine x dx? Say again? A little louder. Okay, it's cosine for sure. What SIGN for that? Negative cosine. Evaluated from 0 to pi. Okay, right? And what is cosine of pi? Actually, -1, but the minus is what makes it a 1. And then minus the minus, cosine of 0 is? Yeah, 1. Okay? And sure enough, that gives us 2. So, we should feel warm and fuzzy inside that our trapezoid rules, with only 4, got us fairly close. With 8, got us really close. With 16, would have been even better. But you never would have actually gotten there. But you kept getting closer and closer, 1.999997 or something like that. After a while, you say, hey, close enough. We'll count it 2. Okay? That's also called the method of exhaustion. You just run out of energy and say, okay, this is close enough, I'll count that close enough. Even for those we don't know the solutions to. Okay? And sure enough, in the book, let's just go on and see what they did. When it's equal to 4, delta x is pi fourths. So that was approximately pi eighths, because remember, you pull out a 2 from that. Sine of 0 plus 2 times the sine of pi fourths plus 2 times the sine of pi halves plus 2 times the sine. And we know what those are. Pi eighths times 0 plus 2 times root 2 over 2, which is root 2 plus 2 plus root 2 over 2 plus 0. Add all those up. Pi times 1 plus root 2 over 4. And that gave you about 1.896, which is exactly what we got. Okay? With delta 8, then with the n equal 8, your delta x is pi over 8, but because you do 1 over 2 delta x, that would be pi over 16 times, and again, sine of 0 plus 2 times sine of pi eighths, which you have to look up. I can't do that one in my head, plus 2 times sine of pi fourths, which we already did, plus 2 times sine of 3/8, which you have to look up, plus 2 times sine of pi halves, which you know, and then 2 times the sine of 5/8 pi, you know is going to be exactly the same as 2 times the sine of 3 pi over 8. So you don't have to redo that one, just double whatever the answer was, and then do the same for the next one, 3/4 pi, double whatever it was for pi 8, because it's the same sign there. I'm sorry, which one it was on? Yeah, 3/4 pi was √2 again, and then the other was the same as sine pi 8. And then put a sine of pi, which is 0. Okay? And when you do that, and let's see, they did it basically the same way we did, I think. Pi 16 times the 2 from the middle there, sine of pi halves, plus 2 times √2, which is this one and that, this one and that, plus 4 times the sine of pi 8, which is that one, 2 here and 2 there. They come up the same, plus 4 times the sine of 2 times 2, the sine of 3h pi, which is the same as that one. And when you do all that and add them up, 1.974, just like what we got. And for that particular integral, you could have found the antiderivative to determine the exact area of the region, and that was 2. So you're getting very, very close. Okay. I'm getting awfully dry of mouth here. And what have we gone for? About an hour and 25 minutes? So we've still got about an hour and 25 minutes or 15 minutes or so left. You want to take a quick break just to get up, stretch, move around, since we've lost somebody anyway. Hopefully. So let's just pause this. I especially just want to go get something to drink because I'm getting drier and drier all the time. All right, trapezoid rule works sort of okay, but Simpson rule is the next that does quite a bit better. Okay? Now, if you think about a trapezoid rule, you usually have a function. And most of the time your functions are curvilinear, right? They're curve functions. And you're approximating that curve with straight lines. Yeah, so to speak. The trapezoid rule. What the Simpson's rule does for you is basically approximated by a second-degree polynomial, not a first-degree, not a linear function, but a quadratic function, which is a parabola, basically. So if you have a curve anyway, a parabola is going to tend to fit it better than a straight line ever would, okay? If you got the inputs fixed, okay? So basically here, now I've taught from several other calculus texts before, and this is the only one that starts explaining Simpson's rule this way. What they usually do, like I said, is the trapezoid rule, midpoint rule, show how they compare to each other and sort of combine them together and come up with Simpson's rule, which does work, and then sort of point out at the end, well, this is sort of like matching it with a parabola. Well, this is starting with the parabola concept, and I'm not sure they're ever going to even mention midpoint rule. So here's what we've got. One way to view the trapezoid approximation, definite integrals, say on each subinterval you approximate f with some first-order linear polynomial. Simpson's rule, you proceed to one step further, approximated by second-degree polynomials, meaning a parabola. Okay? Before presenting Simpson's rule, consider the following theorem for evaluating integrals of polynomials of degree 2 or less. Okay? Now, I don't know. I've not seen them start it this way, but here's what they do it. So here's a polynomial of degree 2, less if a was equal to 0. But if p of x is equal to this, then the integral of p of x would be, let's start with the dx, b minus a over 6. You might say, where does that 6 come from? Hang on, we'll deal with that. Okay? P of A, that's your first value, plus 4 times P of A plus B over 2. In other words, the midpoint between A and B, A plus B divided by 2, 4 times that plus B of B. Okay. Yeah, that's exactly what I think of when I think of an integral of a polynomial. No, I don't even come close to that, okay? So, where kind of did this come from? It's, without dragging on too much, let's just take your word for it for right now, okay? Now, this may help it make it more sense or less, I don't know which. If you do the 2 and the 4 and make this 2 times A plus B, so it's giving some weight to P of A, some weight to P of B, and twice the weight to P of A. No, I'm sorry. This is P of this. You can't do that. P is the polynomial function, and this is the value you're doing in the middle of it. So sorry about this. Evaluate this polynomial at A, evaluate that polynomial at B, that gives you the input values. And then for the point in the middle, 4 times that value in the middle, okay? And do that B minus A over 6. Now, they don't really tell you where that's from, but this is a theorem. That's how a good approximation for a polynomial P, a quadratic polynomial. Just, that's it, okay? To develop Simpson's rule for approximating a polynomial, definite integral, you again partition the interval A to B into n subintervals, each of which is delta x, which is B minus A over n. This time, however, n is required to be even. We never said anything about n before. It could be anything, but it had to be an integer. Now it has to be an even integer, okay? And the subintervals are grouped this way. Well, this seems like it's really bizarre, okay? Remember, your n has to be even. So you have x of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and n has to be some even number, okay? Here's what you're going to do. You're going to take these first 3, so x0, x1, x2. This is going to be your first group. Then you're going to have this group, x2, 3 to 4, 5, 6 to 7. Oh, yeah. Okay, notice you're using the one twice. 4, 5 to 6, that's going to be the next. 6, 7 to 8, 8, 9 to 10. So you always have to end on an even number, okay? Because this is going from 0 to 2, 2 to 4, 4 to 6, 6 to 8. So you have to have an even number, okay? On each double subinterval, okay, x of I minus 2 to x of I, you can approximate f by a polynomial p of degree less than or equal to 2 by that same formula we just had, okay? By that theorem. Let's go back and see it. It's B minus A, this time over 6, okay? Not B minus A over n, B minus A over 6, okay? The first one, 4 times the middle one, and the last one, okay? And you're going to do that for every group like this. First, 4 times this, plus that. This, 4 times that, plus that. This, 4 times that, plus that. So notice, these here we're using twice. Once at the end of this one, once at the beginning of that one. This is 4 times. This one's only once, and that one's only once. All the rest of them. So notice you got coefficients there of 1, 4, 2, 4, 2, 4, 2, 4, and then suddenly, after the last 4, another 1. Okay? Keep that in mind. Okay? So, here's an example. On this subinterval 0 to 2, choose a polynomial of at least degree passing through the points x0, y0, x1, y1, and x2, y2. Okay? So here's your function f, the dark line here. Here's your polynomial approximation here. From 0 to 1 to 2. So start with polynomial here, go up to here to there. Okay? Now that's not going to be a great fit, but it's going to be a lot better than the trapezoid rule. Okay? So there is going to be your polynomial, your quadratic polynomial best fit for that. It's approximately equal to the area under this. See, it overshoots quite a bit here, undershoots a lot less here, but for a long range, you might say. So that's your best approximation. Okay? That's going to be better than trapezoid. Trapezoid would have been there to there. I mean, not going to be particularly great. Okay. Now, each one of these intervals here, 0 to 2, 0 to 4, 2 to 4, 4 to 6, 4 to 8, 6 to 8, every one of them is going to be approximated by that polynomial, which remember was x, your delta x divided by 6, okay, times 1 here, 4 of those, 1 of those. And this is the halfway point between those two. Okay? Now, this x2 minus x0 is twice your delta x, which is b minus a over n. Okay? So that made it 2 over 6, which is over 3. So that makes your coefficient here for trapezoid rule, for the Simpsons rule here, b minus a over 3n to begin with. And then it's alpha of x0, 4 times alpha of x1 plus alpha of x2. You repeat that, 2 to 4, 4 to 6, 6 to 8, 8 to 10, and you'll repeat this one once here. This will be 4 times, that'll be 3 by that time, and then alpha of x4. Then you start the next one with alpha of x4, so you repeat that one again, 4 times alpha of x5, alpha of x6, and keep going, and you lead to the next theorem, okay? You're going theorem to theorem here. Here's Simpson's rule, this is theorem. If f is a continuous function on a to b, it's got to be the case, and none of these work at all, okay? Got to be the case of a continuous function on a to b, including the inputs. N be an even integer. Last time it was any integer, this is an even integer. Simpson's rule for approximating that interval would be this. B minus A over 3n, not over 2n, but B minus A over 3n. Okay? Alpha of x0, coefficient 1, 4 times alpha of x1, twice alpha of x2, 4 times that, twice the evens, 4 times the odds, okay, until you get the last one, then it's just 1 times the last one. Okay. Now, remember our trapezoid rule. B minus A over 2n. That's the first thing you did. And then you did one of these, 2, 2, 2, 2, 2, 2, 2, and one of those. Same type thing now, except it's B minus A over 3n. 1, 4, 2, 4, 2, 4, 2, 4, 2. The next to last is 4, and then 1 again. So basically you do the same type of procedure, just your coefficients are different. Okay? So let's do the same one we did before for both n equal 4 and n equal 8. Okay? So if you recall how we went, let's draw the basic graph here. Okay, there's a sign. This is 0, pi, pi halves, pi quarters, and 3/4 pi. Okay. And n is 4. Okay, there you have it. Okay. Something happened to my pi. Okay, there it is. Remember, this is root 2 over 2. This is 1, and this is root 2 over 2. Okay, those are the values there. Okay. Simpson's rule now, we use coefficient of 1, 4, 2, 4, 1. This is for n equal 4. Okay? So, 1 times 0 is 0. Okay, wait, let's start with this. N minus, so you have pi over, and then you had n equal 4. 3 times 4 would be 12. That's your delta x term, only it's got extra stuff in it, okay? Times. The first one was 0, okay? Because the function value is 0, yeah, so that's all 0. Plus, now it's 4 times this value, so that's 2 root 2, right? Plus 2 times this value, which is 2, plus another 4 root 2 here. I'm sorry, 2 root 2. 4 times 2 root 2 over 2. That's a 2 root 2. Plus 0 again. Okay, so it's pi 12ths times 4 root 2 plus 2. Okay. Now, to make life a little easier, factor out a 2. That would be 2 root 2 plus 1. And that would make this a 6. So it's pi 6 times 1 plus 2 root 2. Okay, someone with a calculator, punch away, see what you get. Someone with a calculator. Pi 6 times 1 plus 2 root 2. Anyone have a calculator? All of you go for it. Check answers. Pi over 6 times 1 plus 2 root 2 in parentheses. Second.
2.0045.
Okay. 2.0045? Is that what you said? Okay. Now look at that. One time, the Simpson's rule for 4, you're already way closer than trapezoid was for 8. Way closer. Trapezoid rule was 1.96 or 1.97 or something like that. Much closer here. Let's see what it'll give us for 8. Now, remember, trapezoid rule undershot this always. Here, a parabola may under or overshoot, so you can't go by the same thing we had before. All right, so let's try it for 8. This time we're putting in pi 8ths, 3 pi 8ths, 5 pi 8ths, and 7 pi 8ths. Okay? Now, if I remember correctly, which I probably don't, this was something like 0. Someone do sine of pi 8ths. Was it 292 or something like that? Sine of pi 8ths. Anybody? Sine of pi 8ths. Second?
0.0068.
You're in, I think you're in, yeah, you got to be in radian mode. You were in degree mode, I bet. 282? 282. That'll be the same over here for this one, 0.282. And also give me the one for 3/8 pi. 0.9, I don't remember what. Yeah, 3 pi over 8.
That's going to be 0.923.
23? I was guessing.
And then instead of 0.282, it's 0.3.
What's that?
Instead of 0.282, it's 0.382.
383.
382.
383? Or 2? Okay, I'm sorry. 382. Okay. My hearing is terrible. Okay. 382. Yeah. Okay. Let me try this one more time. 382, and this will be a 382. And this will be a 0.923. Okay. All right. So Simpson's rule for n equal 8, this is S8, we'll call it. We'll start the same way we did before, pi over 12. Oh, wait, no. It's b minus a, which is pi, over 8. But 8 times 3 is 24. So that would be pi 24ths times. 0 is going to be the same. Okay, there's just one of the, oh. Go back and change my coefficients, because we've got more points now. Okay? You got to do this every time. It's 1 times that one, 4 times this one, 2 times this one, 4 times this one, 2 times this one, 4 times that one, 2 times that one, 4 times this one, and 1 times that one. Got to get our coefficients right. 1 times 0 is 0. I can do that one. Okay, plus 4 times 0.382. So if someone, that's 1.4. Goodness gracious, the head isn't working today. No.
4 times 0.382.
Yeah, you could just put this in the calculator. 4 times 0.382 plus square root of 2 plus 4 times 0.923 plus 2 plus 4.923, I should have doubled that to begin with, plus root 2 again, plus 4 times 0.382.
Yeah, you lost me a little bit there.
I'm sorry, okay,
You
slow down.
lost me a little bit there.
Okay, yeah, let me go more slowly. I'll do it more smartly too. 0, that was that. Let's do 8 times this one. 8 times 0.382 plus 2 times root 2. But you got one here, you got one there.
Each separate one of these in parentheses.
What's that?
Like each multiplication portion do it within parentheses. Like 8 times 0.382 is in parentheses. And then
Yeah, just however you enter it on there. Okay, 8 times 0.382 plus 2 times root 2 plus 8 times 0.923 plus 2. Because I did this side and that side at the same time.
plus 9.
Second?
Plus 8 times 0.923.
Yeah, 8 times 0.923
And then what was the last
plus
one?
2. Did you get that last one? Plus 2. Okay, and do that times pi over 24. The sum of all those times pi over 24. Could have made life easier had I thought of something else for it. Let's see what you got.
That first part was 8 times 0.382.
Okay, yeah. Let me go back and change again. Sorry about this. Okay. Because everything is by 2 here, we can do that by pi over 12. So we're going to do that to begin with. But let's see. Yeah. All right. So let's back off and start again. Yeah. Okay. 4 times 0.382 plus root 2
Plus root 2.
plus 4 times 0.923 plus 1, just 1. Do it equal sign.
So 7.6.
Okay. then multiply by pi and divide by 12.
1.998.
Second.
1.9986.
Okay, wait. Call it out to me. 1.99.
863.
Second.
863.
363.
863.
863. Okay. Okay. Now, it doesn't look that much better than this one. It's a little bit. But I'll tell you where our error came in. See, we got that within 3 digits already. That's within 3 digits already. We only rounded these to 3. We really needed to take these to 4 or 5 or 6. So we're not ever going to get much closer. But if we had done a more precise number here, 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 and here, those two, then we'd have got this one way closer to 2. Because you can't get any better output than you have input. And we already got within 3 digits there, but that's because we only put in 3 digits there. So if we had put in 4 or 5 digits there, I'm sure we'd have gotten 4 or 5 digits there. Let's see what the book got off of that one. Let's see, they're going to show it here anyway. So let's do it, okay? I'm going to have to erase what I got. Otherwise, you can't read it. Okay, when n equal 4, this is what we had. Remember the pi 12ths, that was pi minus 0, pi, over 3 times your n was 4, so 3 times 4 is 12. Sine of 0, 4 times sine of pi 4 is 2 times sine of pi half, 4 times sine of 3/4, and that's going to be a 0 again. And when we did those, and those were exact, 2.005. Well, I've already erased ours, but we were even more precise than that. But anyway, much better than trapezoid rule at 8. That was already way, way better. Okay, now when you do it for n equal 8, they say you get 2.0003. So every time you double this, you get at least 1 order of magnitude better. It's a little bit better than 1 order of magnitude. So you're close enough to 2 there by anything. I think anyone would have rounded that to 2. Okay? We didn't get quite that close because of round-off error earlier. If I'd have left it so you didn't do a round-off, you actually entered sine of 3/8 pi and did that, you would have all the digits you needed. But that was just a bit too much. Okay, so let's look a little bit at the error analysis here. Okay, when you use an approximation technique, it's important to know how accurate you can expect the approximation to be. The following theorem gives the formulas for estimating the errors involving the use of the Simpson's rule and the trapezoid rule. Why they said it that way is trapezoid rule and Simpson's rule down here. If f has a continuous second derivative on this interval a to b. Now that wasn't a requirement before, but to get your error estimate, that is a requirement, okay? Continuous second derivative on the a to b. Then the error e in approximating this integral that you can't integrate anyway, that's the f that has to have a second derivative. Now using the trapezoid rule, that absolute error, that's part of the absolute error bar, it's going to be less than or equal to b minus a, that's your interval cubed, over 12n squared times the maximum second derivative on that interval a to b. The maximum value that second derivative can have on a to b. Now, sometimes that will be an endpoint, and sometimes it will be somewhere in the middle. Quite often you'll find it's going to be an endpoint. Okay? Moreover, if f has a continuous fourth derivative on a to b, then the error in approximating this by Simpson's rule, fourth derivative now, the absolute value less than or equal to b minus a to the fifth, which makes that a bigger number here, but look at your coefficient, multiply or divided by 180, that's more than 10 times more accurate there, n to the fourth, bigger the n is, I mean, that's really making that small, kind of the maximum of the fourth derivative when x is between a and b. And again, quite often that's going to be at an endpoint. Not always, but quite often that's going to be the case. Okay. And that's Simpson's rule. In general, when using an approximation, you can think of the error as being the difference between the function and the approximation. That's a good estimate of what the error is. Theorem 8.6 states that the error generated by Trapezoidal rule and Simpson's rule have upper bounds dependent on the extreme values of your second derivative and your fourth derivative of the interval a to b. Furthermore, these errors can be made arbitrarily small by increasing the n, providing the f double prime and f to the fourth derivative are continuous and therefore bounded on AB. So that's a requirement for your error bounds that we know. So here's example 3. Determine the value of n such that the trapezoid rule will be approximate the value of this thing with an error that is less than or equal to 0.01. How would you begin? I'll do the first step. Let f of x equal 1 plus x squared to the 1/2 power. That's your function. Okay? Now what do you reckon you're going to do to the function? Trapezoid rule. Trapezoid rule. Error bound, maximum of f double prime. So we need to take second derivative of f. So where do you start? First derivative of f. What would that be? A little louder?
We'd use the chain rule to start with.
Chain rule, yeah, exactly.
So like u to the 1/2.
Say that again.
Take the derivative of u to the 1/2 to start with.
You write down 1/2, is that what you said?
So like substitute u in for 1 plus x squared, and then take the derivative
Okay.
of that.
My hearing is so rotten. Okay, tell me what to write. One step at a time, it's going to be fine.
I said substitute u in for 1 plus x squared.
Okay. All right. You're saying 1 plus x squared is equal to u. I understand what you're saying now. U, okay. And then what you do, 1/2 u to the negative 1/2, and then you do
Multiply that by 1 plus x squared.
by what?
1 plus x squared.
Oh, okay.
Alright.
It's not multiplied by that. You're on the right track. What you do is u prime.
Oh, okay. So just 2x then.
Yes, multiplied by 2x. So this would be 1/2, and your u is that, so it would be 1 plus x squared to the minus 1/2 times 2x. Okay. Okay? Yeah. Now, that 2 and that 2 will go out, so let's just write it down as x over 1 plus x squared to the 1/2. Okay? I don't know if it's any better that way. I really don't like it better that way, but that's basically what we're getting at. Okay? But we need second derivative. So we need to go one more. And I think I prefer the previous one. So you can do product rule or quotient rule. It doesn't matter. But I kind of prefer the product rule, so that's going to be x times 1 plus x squared to the minus 1/2. Okay? And we'll take a second derivative, f double prime of x, of that thing. Okay? And using product rule, what would that give you?
So you would start with 1 times.
Okay, you're starting with derivative of the first, so that's 1 times this, 1 plus x squared to the minus 1/2, right?
And then plus x.
Plus x times,
Whatever the derivative.
okay, I'm going to, let's see. This thing is driving me nuts. Okay. All right. To do the derivative of the second, okay, that's going to be negative 1/2, 1 plus x squared to the minus 3/2 times another 2x. Okay. Now, that double prime will be, and I don't know if this is how I want to leave it, but I'm going to do it this way to begin with. 1 over the square root of 1 plus x squared. And that's going to turn into a minus sign, I'm pretty sure. Okay? Because of that minus 1/2 there. But again, the 2 will go into 1/2, so that disappears. Minus, and then you'll have an x squared over the square root of 1 plus x squared cubed. Okay? I believe that's taken all the pieces into account. And if you wanted to rewrite that as 1 plus x squared, you see this thing squared is just that, minus 2x squared over 1 plus the square root of 1 plus x squared cubed. Okay? And then this, of course, just goes to minus 1. So this is 1 minus x squared over square root 1 plus x squared cubed. Okay. I think I did it all right there. Okay. Now, you want the maximum value of this between 0 and 1. Okay? So, at 0, this is going to be a 1 here and a 1 here, so that's just going to be 1. Okay? At 1, this would be 0. Now, I'm just going to hazard a guess that that max is going to be at 1. I don't know that for absolutely certain. I mean, x equals 0, the maximum would be 1. Because I don't really see any way around it. Because you put in larger values here, and this gets smaller, and this doesn't get much smaller. It does get smaller. I don't know. So let's see what they say. They say the maximum value occurs at x equals 0. So that's just going to be 1. So your error bound here, from what we had before, is equal to, go back here and see, it's equal to that interval, b minus a, in our case 1 cubed, which is just going to be 1, over 12 times n squared. So it's 12 times n squared times the max of that. And the max of that is 1. Okay. So we want this to be less than or equal to that. Well, they told us less than or equal to 0.01. Okay. So we want this to be less than or equal to 0.1. Okay. Then let's multiply both sides by 12n squared. You have 1 is less than or equal to 12n squared, only it's going to be a 1.2n squared. Wait. 0.12n squared. Okay? Okay. So divide both sides of this by 0.12. Okay. So 1 divided by 0.12. What does that give you? 1 divided by 0.12. Second?
8.3.
Okay, 8.3. Okay, I would say, and take a square root of that, because that's n squared. Okay, so the n would then be exactly 2.88, blah, blah, blah. Round that to 3. Always round up to give you a little more cushion. Okay? All you need is 3 for the trapezoid rule and n equal 3, and you're going to be within that. Let's see if that's what they got. Yes. Okay? Now, that's all we have to do on that. I thought they were saying Simpson's rule as well. Okay? Because n equal 3 is going to give it to you with the trapezoid rule. So that one was pretty easy. They could get a lot more complicated than that. Okay. That finishes 8.6. By the way, all the odd number answers are in the back of the book, and they're worked out at calcchat.com. Tutorial help and worked out solutions are there. And there's even fuller solutions to the more description and indication, interactive type stuff with the calcview.com. So do any of the odds 3 through 13. They're all at CalcChat and in the back of the book, and number 3 is at CalcView. Do any of the odds 15 through 23. They're all at CalcChat. 17's at CalcView. Do either 25 or 27. They're both at CalcChat. 25's at CalcView. 29 or 31. They're both at CalcChat. 29's at CalcView. Sorry about that. And then estimate using, technology. Try number 33. It's at CalcChat also, not at CalcView. And try number 35. It's at CalcChat, not CalcView. 37. I would say do either 35 or 37, or both if you like. 39 is think about it, so you can think through that a little bit. Number 41 is a surveying type problem, which I don't know if any of you are civil engineers. Are you? Pre-civil engineering? Okay. You'll definitely be doing surveying there. Maybe some of the other engineers might, but civil I know will be. 43 is a work problem. 45 is in Simpson's rule. 47 is a proof. You can do that if you like or not. Okay. And then, wait. Let's see how they, I'm sorry, I should have done this first, how they proceed with this one. By letting f of x be that, finding the second derivative, they first write that as 1 plus x squared to the first power, to the 1/2 power, then take a derivative, and that gives you this, which is exactly what you got. Then take the second derivative, which gives that. And I don't recall ours turned out quite that simple. Did it? I've already erased it. I don't think I have it up there anywhere. I didn't think it came out quite that simple, but that's what they got. Didn't we have? Let me just see. This is example 3. Oh, no, I'm sorry. Wrong section now. They said that. I may have messed up ours a little bit, but we got the same answer, so we weren't off by much. I'd have to go back and check, but I don't really want to. Okay. Maximum value of that on 0 to 1 would be f of 0, where it's 1. And we got exactly that answer too. Therefore, we can write the error bars as b minus a cubed over 12n squared, f double prime, maximum value of f double prime of 0, which is at 0. And that would be 1 over 12n squared. And we want that to be, okay, we got it, less than or equal to 0.001, okay? 0.01, okay? So they did it not quite the same way we did. They just wrote that as a fraction form rather than a decimal form. We got the same answers, and it came out the square root. We did the square root of 1 over 12. They did 1 over 0.12. They did 100 over 12. Gives you the same thing, 2.89. Round that up to 3. Okay? And, oh, is that in the problem too? That's not I've read my problem well. No, they proceeded to do this, okay. Choose n equal 3, tells me greater than that. Apply the trapezoid rule. And that would be, and we didn't do this. Trapezoid rule, remember, is the difference here, 1 minus 0, divided by 3. So that would be 1 divided by 2 times 3 is 6. And then you use this one once, the midpoint twice, and that would be halfway. The midpoint here, between these two would be 1/2. No, sorry. It's n equal 3. Okay, so 1/3. 1/3 of the way between there would be 1/3 squared, which is 1/9, plus twice the square root of this plus 2/3 squared, which would be 4/9, and then at the end just use it once, and that would be 1 plus 1 squared. Okay? And that would be 1 plus 1/9 is 10/9, square root of 10/9, plus 2 times the square root of 1 plus 13/9, the square root of 13/9 plus the square root of 2. When you do all those together, that comes up. They don't show an answer, do they, on the next slide? Yeah, 1.154. Okay. Now, if you went back and actually integrated that, which I think you can using a tangent substitution, you get 1.164, and we got 1.11144, which is less than 0.02. I thought we were shooting for less than 0.01, but it seemed like they got it, did they? That's when I should have made the assignments. Okay. I've already made them. So we're ready now for 8.7, which in reality, yeah, you may get a package that does numerical integrations for you. Okay? Or, if you don't have those readily available, well, I'm sorry. Those are the ones you can't do whatsoever, okay? But for those who look close, you can use tables, okay? And continuing with integration techniques and improper integrals, so we probably don't do the improper integrals. Let's just get some practice using the tables, okay? Now, most of you are pre-engineering, right? Some of you may be computer science, right? Yeah. Okay. But the others of you are pre-engineering. When you go, and they used to call it the EIT, Engineering and Training Exam, but I think they call it something else now, don't they? That you take either before you graduate or shortly after you graduate. Don't you have a test to take? Here at Lawson, probably wouldn't know about it. Those are in engineering schools are going to it. Check out. There's something that may be called the P2, or they have a new name for it, but it used to be called EIT. And you go in there and you take whatever books and tables and everything you can take with calculators. I just don't know if there's a limit to what power of calculators you can have, but you can take anything you want to for those tests. And they are big, long, hairy tests. The thing is, I don't think you can take a numerical integration package with you. But you can take tables of integration. I may be wrong on this. Maybe you can. But quite often you can have the tables. Okay? Now, ultimately, in your engineering lives, you'll then take the PE exam. And the EIT, or whatever it's called now, qualifies you after so many years of experience to then take the PE exam, professional engineering exam, in your particular major. Okay, and then again, you can take all the stuff in there you want, but I don't know if you can take a numerical integration package. Maybe you can. I don't know what they go to now, but I know you can take the tables. So what we'll do, we'll find indefinite integral using a table of integrals. We'll find indefinite integral using reduction formulas, and we'll find the indefinite integral involving rational functions of sine and cosine. Okay. Well, I know exactly what to talk about. The last one, I can picture it, but I can't think while they're doing it. Integration by tables. Many people find tables of integrals to be a valuable supplement to the integration techniques discussed so far. In fact, they do them for you, okay? The tables of common integrals can be found back in Appendix B in your book. These integration by tables is not a cure-all for all the difficulties that can accompany integration. Using tables requires considerable thought and insight and often involves substitution. So it's not just one thing is going to magically work. Each integration formula in Appendix B can be developed using one or more of the techniques that we have just done, okay, to verify several of the formulas, okay? For example, I guess this is Formula 4 at the back. If you have something that looks like this, okay, then that can be done by substitution, okay? Now, it's probably not immediately obvious how you can do it by substitution, and it's a pretty long, involved process, but it can be done, but that's what you're going to get at the end, and it's pretty easy just to fill in the blanks, you know, A, B, and U, and that kind of stuff. No, actually, they said partial fraction, yeah, partial fraction, for sure. But I think maybe even substitution might really work too. This one here is going to be a trig substitution, a tangent, okay? Is one way. But then the next one, once you get from here to there, then you turn around and do another substitution here. And that's substitution. Okay. So you see you might have several steps to get anywhere in this problem, or a problem like that. Why they pick such bizarre ones to start with, I don't know. Okay. Let's pick one from your text here. See what they're going to do first. Yeah, this is just not following the book. Okay, let's back up one. They do show you some they don't show in the slides here. I don't know how much of this to repeat. I hope not too much. The integral of x log x dx. Does anyone remember how we did a problem like that?
Differential by parts.
By parts, for sure. And it wasn't really all that bad, okay? And yet they show you what to do in a table, and it's fine. You can just look it up immediately and see what it, well, no, they just said integration by parts, okay? This one, on the other hand, what would you do with that? Substitution. Let u be log x, du is 1 over x dx. There it is. Okay? Plug back in and see what you get. Okay? How about this one? Integral of 1 over x log x dx. Okay?
That's still substitution.
I think substitution probably is the way to go on that. Let u equal log x. Du is 1 over x dx, which you got there. And then you got 1 over u du. And yeah, you go from that. So that's not too bad. Okay? And 1 over u du, by the way, is another log. So it's a log of a log. Yeah. Here we go around. But what about this one? Now this looks fairly simple. Integral of x over log x dx. Don't rack your brain too hard. You ain't going to get there. This is not doable by any of the techniques we've used so far. Okay? Now, will you find that in a table? I'm guessing not. I guess you go back to Simpson's rule, probably, or something like that. A numerical integration package. Okay. And then they talk here, that's when they get into these. And but all these you could do another way, okay? But here are some things. Note that the integrals in Appendix B are classified according to the form of the integrand. Several of the forms are going to be a power form. You know, you can do just about all those without going to a table, I would think. But if it got hairy enough, maybe not. This is a polynomial form, specifically a quadratic form. And again, it's something you can do right off the top. This one, though, I'm sorry, this one, it may not look exactly like this. That could be a 17 plus or minus, 3/8 squared. Well, your u, you have to do some manipulation to get it into a form that looks like this, from whatever your problem is. Same thing with these. Those are pretty straightforward most of the time. That's going to be generally a secant substitution. That's pretty easy, those, but then you get more complicated forms of that, it can get a lot more complicated. That one will be just a square root without a square underneath it. There's a square root with a squares underneath it. The trigonometric functions, inverse trigonometric functions, exponential functions usually are pretty easy to fiddle with. Logarithmic functions sometimes aren't too bad, but they can get pretty complicated pretty quickly. Okay? Here's example 1. Okay? Now, let's not try to figure out what technique will work. Let's use the table. Okay? And the table is, do any of you have a book? None of you today? Oh, 1. 2. Okay. Oh, yeah, you got yours. Yours isn't. Oh, yours is. Okay, you got it. Huh?
Mine's just the one on the computer.
It's what?
Mine's just the one online.
Oh, okay. All right. If you turn back to Appendix B, finding Appendix B is the hard part here. I liked it when they put them on the very front, back, well, I thought it was back here. Okay, there's an index at the very end. There's the answers in the next part. You have to get out of the answers. Wait a minute. No, the answers are Appendix A. Where is Appendix B? This is a very small table. Okay. No, I was wrong. Still got to find Appendix B. Through all the answers, since they were numbered A, I guess A is for answers, not appendix. Okay. Okay, here we go. Appendix A is on, find in your text, page 1128, okay? And then the next starts your appendices. The first is proofs of several theorems. I know you want to read those. But then B is your integration tables. That's where we begin. So, what kind of form is this? I would look for U root U minus A, or something like that. So look back here. It says forms involving U to the n. That. Forms involving A plus BU. I don't think so. Okay? But look at that a little bit and maybe you do have it. Yep, look at number 11. Nope, you're going to have a square root involved there. So go down to the fourth group, forms involving the square root of A plus BU. In our case, let's see, before I say that, let me go back. Yeah. In our case, the A is going to be minus 1, and the B is going to be 1. Okay? And then number 17 is close to being it. I think that's as close as we're going to come. Because all the rest of them with square roots have squares in them. These do not. Okay? So I think this is going to be number 17. All right. Don't let me go over. Okay. Here's what number 17 tells you. It tells you that the integral of 1 over U times the square root of, I'm going to write this as BU plus A. Doesn't matter. Everything is the same as what we've got, okay? DU. It tells you that answer is one of two possibilities. Yuck. Yeah, that'll be fine. Okay, first, what is our A? Our A is minus 1. Okay? So that means A is less than 0. So in the back of your book, that's the second one given, which is 2 over the square root of minus A, which our A is minus 1. So that's going to be minus a minus 1, which is plus 1. That's going to be easy to do. Inverse tangent, I like to do inverse tangent. They like arc tangent. Square root of, our A is minus 1, so it would be, but our BU is the same. That's just x minus 1 over 1 minus a minus 1, okay, plus c. Okay, so basically this becomes 2 times the inverse tangent of the square root of x minus 1 plus c. Okay, and let's see what they got. 2 inverse tangent square root of x minus 1 plus c. Perfect. So you have to arrange, and not a bad idea to write down this kind of stuff too. Here our A was minus 1, our B was 1 to get into that form, and our U was x, which is exactly what we got here. Dx, everything works out. I would write it all down for a while, but you know, after doing it for a while, you can see which ones need to be written and which ones do not. Okay? So let's see how they describe doing it. That's how I did. Let's see what they do. Because the expression inside the radical is linear, you should consider the square root of a plus bu. Okay? And number 17 that we used in the back with a less than 0 would be this one. And they did exactly what we did. I think I would have done a little more filling in the blanks here. Your u is x, your a is negative 1, and your b is positive 1. Then fill in these values. 2 over the square root of negative 1, which would be plus 1. That's just going to be 2. Inverse tangent, or arctan, of the square root of exactly what you had in your form. A plus bu, that would be your square root of x minus 1. Over a negative 1, negative a, and your a was minus 1, so it's over a plus 1, so that's just square root of x minus 1 plus c. Okay, and they now is when they indicate that a equal negative 1, b equal 1, u equal x. And that gives it for you. 2 arctangent square root of x minus 1 plus c. Okay, they don't do example 2, 3. So do we have time? I think not. So I think next time we will start with example 2. And let's look ahead. It's about time to do that. Okay. Homework exercises. We didn't get many done here. Try to do number 3. That's both in CalcChat and CalcView.com. And 5 I think you can do. Hold off on the rest of those. We'll do them later. Okay, where are we going to go from here? I really don't think we have much time to do improper integrals. So I may give you a very quick slideshow of that just to get you familiar with it, but then letting that be something, I'm not going to test you on it. We just don't have time for that. And that almost gets us to the end of the chapter. So next time we'll finish 8.7, and then I'll do a quick slideshow on 8.8, and I'll give you the test for chapter 8. Okay. Then what will we do? Chapter 9 is infinite series. I know we have time to do 9.1 and 9.2, and I think that's all I'm going to have time to do in that one, because we really need to get to Chapter 10, which I know that you need. This, because 9 is one long chapter. Okay, 10. Okay. I'm pretty sure parametric equations, polar coordinates, you need. Now, they mention here conic sections. And we'll do just a slideshow of that, a very quick slideshow of that, because that's really covered a little bit more in Cal 3. So, but I'll introduce you to at least to get enough to get you in trouble there. But then we'll get into 10.2, we'll go full blast, 10.3, full blast. I can't remember, do we have to do polar coordinates? I just can't remember if that was in our, seems like that's in our course description. Okay, that's 10.4. I don't think so, maybe not polar coordinates. Okay. Okay. Now, I'm trying to remember vectors in the plane. I think we need to get into 11 too. So what I'm guessing, we'll just do a couple sections in 10 and then get into 11 and try to finish the term in 11. I just don't want to get into Cal 3 yet, but I don't think Cal 3 shows up until we get to 11.6. And then Cal 3 begins with 12, yeah. So I think that's where we go. So we're only going to do, I'll give you the test on Chapter 8. Infinite series, maybe 2 sections. Chapter 10, maybe 2 sections. Chapter 11, 2 sections maybe. And then we'll have a test on that one. Yeah. And we'll cover as much as we can in that. And I think that'll pretty much wind up the term for us. I believe that's what I said at the beginning. Let me go back and look. 126 is Chapter 7, that's where we began. Chapter 8, that's what we're just finishing. 2 sections of Chapter 9, 3 sections of Chapter 10, and as much as we can cover in Chapter 11. And we'll have to stop there. So the last test will be, well, I don't know. Maybe we'll do 1 test on the 5 sections in 9 and 10, 2 and 9 and 3 and 10, and then the last test will be Chapter 11. So that's probably the direction we'll go. Oh, good deal. Sorry that took longer than that. Good deal. Second test coming, first test coming in. By the way, research papers, folks. This is my very best, biggest class, and I've gotten only one paper in so far. Please get me your papers. All right, take care.